坐在那边会不会拍到头啊？
应该不会，我都坐这啊。
没有，你之前好像他们都坐在中间。
会吗？
一点点。
还是我多旁边？
印象中好像要坐在。
不过下面那个字如果没有很重要用到，它其实
应该。这边的。
这样就可以这样。
哦。
对，因为刚好它是画面的背景。
移一下。
可以，你移到那边看得到这里。
没关，应该要这两个相机要在这边的话。
你太久没来了哈。
1个月。
通常电脑跟你的人在中间，像摄影机。哇。 这个电池是6块钱的。这个电池是6块钱。
我看一下这边有没有亮灯，是这边应该剩2个，
看好像是最后一个。
好。
你用的这么快啊？啊？用的这么快？我记得你上礼拜3不是才？
对啊，才换1次而已。
对，上礼拜3就只有1堂课。
对啊，对啊。
用的这么
而且只有1个小时。
对啊。
我想会不会这期间还有其他人拿去用之类的？
上面贴的是电磁学专用。哦，被偷用。提醒我中间下课，我可能换这个电池。还有5分钟。平均只有30-40。
我目前改到的啦。
不，你改了几分嘛
？20多。
不是，你改的占总分的多少？
哦，那些差不多全部。
你说整份平均30-40啊？
对，因为我就是分2份，然后各改1份这样子。
哇，这么惨啊！
就大部分都是传输线那边分数都拿不太到。
奇怪。
我是应该先把声音关掉。
啊，我已经关掉了。
哦
OK， 好，把它关掉。怎么会？因为过往其实是至少去年那一届平均是75还是？
不知道，也有可能我们有改比较严啦，因为就是想他们是翻书，所以就改的比较严格一点。
对，因为已经 open book 了。
对。因为后来实际算一算，就算扣掉传输线，然后最后面那题至少要拿个50-60分，但是。
不，你们不会改错吧？或者是学生的答案是对的，你们是错的？
就是这是另外一个问题，就是因为其实有大部分其实他们是直接只写个头，后面就不写。
只写个头。
对，就可能写第1行之后，他们下面就不会了，然后就没办法改。然后有写完整个过程的，其实我再帮他按计算机，我再帮他算过1次，所以理论上应该是不会改错。
那第1题送分题，25分观念题应该 OK 吧？
大概15到20分吧，就是得分率来讲的话。
那15到20就代表是，第1题是20还是
25？25，因为有5个小题啊。
25里面拿到15到25，那就差不多一半到80。 那应该平均也要6、7个吧，好恐怖哦。所以是怎样？他们并没有认真上课，线上观赏就随便乱来的。唉，太长。所以远距教学还是不可行的。Impedance matching 是不是没有人对
？1、2个，就是也是少数的那一种。
可 impedance matching 过往每年都考啊。
就是有写的人大概都会对，但是没对的就是没写的。
所以他直接放弃。
就是他可能就是先把那个反射系数算出来之后，后面就开始乱写或者是不写。对。就有些人会写，但是他就是会错一点，就是可能他角度带成进度或就带反带错，就是一点小错啊，但大致上观念是对的。
可角度带进度全部答案就错了。因为它要算长度嘛。
对。
当你角度带成进度的时候，
就是没有，它是式子有列对，然后就可能就是小错，但是它其实后面有
就只扣1点分嘛。
对，因为它答案出来是对，但我不知道从它就可以数字带。
好吧，我们准备。Okay, so let's begin. A quick recap to what we covered last week. But basically, we can just classify or we can describe a given dielectric material by 1 plus chi. This is induced polarization. So we can coin certain dielectric material by the simple constant, the relative permittivity, or we can just multiply this relative permittivity by epsilon 0, which is the vacuum permittivity, and we just call it the absolute permittivity, epsilon. And I personally recommend it for you to memorize this relation between the flux density and the E field intensity is the flux density remains the same throughout the space. And if you have certain material, then locally the field intensity will be reduced by a factor of epsilon. So before we move on to new materials, let me try to elaborate this equation in more details. So let's come to the blackboard. So in space, I have lots of free charges. I have positive charges, I have negative charges, right? So these are the free charges. The associated field will be therefore D, okay? So I can draw a lot of field lines. Ideally, this should be straight lines. Forgive me if these are not really straight. Okay? So this is in free space. I have lots of free charges. So in this case, in free space, I can write my E external. This is like my externally applied field. And this is D divided by the vacuum permittivity. Okay? But somehow, I can insert certain material, right? Suppose I have a slab of glass with certain thickness. In this case, I ask myself, within this material with epsilon, absolute permittivity, I ask myself, how many field lines do I have that are due to the free charges? the number remains to be 6, unchanged, right? The field lines due to the free charges, my externally applied field, remains the same. But what is reduced is, due to the induced dipoles, I might have, well, say, 3 pairs of induced dipoles. And each one of them are producing some counteracting field lines. And therefore, some of the field lines due to the free charges are being cancelled. Thus, my E field intensity within this material is weakened by a factor of epsilon, right? So the major difference between D and E is D is related to the free charges. So basically, even though you are within such a material, dielectric material, where your field is weakened, but the field lines due to the free charges remains the same. It's only you have produced, oops, negative sign, positive sign, right? You have induced certain pairs of electric dipoles that itself generates a counteracting E field lines to make the material having weaker electric intensity. Okay. So now let's take a good look at one example. This is something very similar to what we covered for metal. Well, if you still remember, when we analyzed metal, we had a thin shell, right, of metal, but now we just replace the material, the same shell, the same geometry. You have a positive charge at the center, and you have a shell, but now the shell is made of dielectrics. Okay? So this dielectric is having a relative permittivity of epsilon r. Still, the inner radius is Ri, the outer radius is Ro. So this is, again, a 3-dimensional spherical shell. Okay? So now we want to analyze what are the resulting electric field intensity. Okay? We're still dividing the analysis regions into 3. When we are outside of the shell, when we're within, standing inside the material, and really inside of the shell. Okay? Still the same 3 regions. And we're still applying Gauss's law. Well, when we're really outside the shell, the E field intensity multiplied by the enclosed spherical surface, 4 pi r squared, is Q divided by epsilon 0. When we're standing outside, right, we don't have relative permittivity, so we use epsilon 0. And the amount of charge being included is just Q. Right? So this is nothing new. The problem arises when we are standing inside the shell. Okay? Now, in this case, when we're inside the shell, you might be wondering, well, how many charges are being enclosed? But the benefit of defining a dielectric material using epsilon, the benefit is you don't really have to care about the induced dipole charges. All you have to do is include the relative permittivity. Okay? So for a Gaussian surface with the radius r, r is greater than ri, but smaller than ro, the spherical surface is still 4 pi r squared, but now you retain the charge because eventually you're still enclosing this free charge of Q, but all the effects of the induced dipoles provide some counteracting charge densities as well. So initially you might be thinking, oh, this Q has to be subtracted by some other amount of induced charge. But that's not really necessary. All you have to do is you include this relative permittivity of that given material. And that weakens your E field intensity inside the shell. Okay? So in this case, when we are inside the dielectric shell, the E field intensity, the strength, is weakened by a factor of epsilon r. And this is due to the existence of the induced electric dipoles. Okay? So therefore, starting from this point and onwards, when you meet a given dielectric material, all you have to do is include its corresponding permittivity. And you can truthfully derive its E field intensity. Okay? Now, as we walk closer into the inner radius of the shell, again, you recover the very similar result. Okay? Here, again, you're in vacuum, so you don't need to include epsilon r. For vacuum, epsilon r is 1. Okay? What does this mean? If you plot all these results of E field intensity E, you will see two abrupt jumps. When you're outside, you have a very smooth 1/r² dependence, right? So as you move closer to the shell, you have an increasing E field intensity. But once you reach the boundary, the outer boundary, and you step across it, you have an abrupt jump. Okay? And this is exactly the effect of the induced dipoles, right? So when you are outside, you have a very smooth, varying E field intensity. At the boundary, it's continuous, right? But then you have abrupt jump. But once you're inside, you have, again, a smooth variation. But when you reach the inner radius, where you have the dielectric vacuum interface, that's where your dipole ends, right? Inside the vacuum, you have no longer any capability to form induced dipoles. And therefore, at this inner radius, you have accumulated some kind of induced polarization surface charge density. Okay? So once you step across it, your E field strength is immediately increased. So whenever you have interfaces, like one interface here, second interface here, you should always expect to have abrupt jumps in the E field intensities. Okay? One jump and two jumps. But now you ask yourselves, this is plotting E, right? This dashed line is ER. Okay? What about the D field? The D field, the flux intensity, flux density, is only associated with the free charges. Okay? It does not feel the presence of the induced dipoles. Right? So if we plot out D is continuous and smooth throughout. Just like the case I drew on the blackboard. For D, when even you have the interface, you have material difference, it's not changing. D is a smooth, varying function. It does not care for the induced dipose. So in this simple case, we don't have any spatial dependence. If we have infinite charges, we have a constant field, right? And therefore the D is not a function of space. But what I'm trying to tell you is D is a smooth varying function. So in this case, we have a single charge. It is setting up some kind of field or density pattern, which is decaying, well, as a function of the distance. But for E, you can have abrupt jumps, but D remains smooth throughout. Okay? So that's a major difference between D, the flux density, and E, the field intensity. So E can have dramatic changes, but D cannot, right? The reason is, even though you're standing inside this shell, when you evaluate D, you're only asking, well, how many free charges do I have? The answer is, I still have one. It's the same. But when you're standing inside and you ask, how strong is my E field? E field is asking, how much of the net charge do I have? Right? The net charge means I have the free charge, I have the induced charge densities. So when they add, you actually have a reduced value. Okay? Right, so basically, mathematically, D equals epsilon E. Therefore, D is really not material dependent. Right? So now looking at the math, you should be satisfied because Q divided by 4 pi r squared is not material dependent, right? So throughout the space, it should be very smooth. On the other hand, E, once you have epsilon 0, and now in the back of your head, you should be very alerted. When you have a dielectric material, you have to fill, you have to multiply by epsilon r. Okay, so E is material dependent, D is not. Right? So for this case, you can also calculate, well, how strong is the induced polarization vector. You have a sudden drop in the E field intensity. It means you must have induced polarization vector. Okay? So the induced polarization vector looks like that. Why? Because by definition, the polarization vector is the difference between D and epsilon 0 E. Okay? So in this case, within the dielectric shell, you have induced a polarization vector in the direction of the radius with that amplitude. But it is also a function of space. It is a function of the radius. Okay? So the only difference between a dielectric shell as compared to the previous case, a metallic shell, is you have this polarization vector. And you have a non-zero E field intensity. If you have a metal, you have zero field inside the metallic shell. All right? So that's a major difference. Okay. So now I want to talk about boundary conditions. This is probably the part most confusing to a lot of students. So whenever we talk about boundary conditions, the problem we are trying to solve is we might have multiple or various different materials, right? So in this case, I have vacuum, I have a piece of maybe glass, then I form an interface, okay? I form one interface. So if I erase all this, right? The real problem that we're trying to solve is, well, for example, I have material number 1, okay? And I have material number 2, and I can have even a third material. Look at your cell phone, right? The light is coming out of your cell phone, but your cell phone is covered by a piece of glass and some anti-reflection coating, and then you always have this protective plastic tape or something, right? So this might be your glass, reflection coating, and your piece of protective coating, or your whatever you call it, right? The thing you stick onto your cell phone, right? Now the question is, well, if I have some field, right, making an angle to the first interface, do we have the capability to know what is the outcoming field? Well, this is epsilon 4, right? And this angle. Well, this happens every day. Even for light, think of light as the E field. Well, light penetrates through a lot of medium and reaches to our eyes, right? But do we have the ability to calculate it? For this very practical problem, we need to understand about boundary conditions, okay? And the boundary conditions is nothing really new. It's really just another a recap of the fundamental postulates. Okay. Okay. Now we have medium number 1 and medium number 2. When we have two materials, we form one interface. Okay. So ideally, this interface is a two-dimensional surface, but we're only plotting the cross section. So this interface is represented by a single line, but it's actually a surface. All right? Whenever we form an interface, we need to think, how are the fields classified relatively to the interface? Once you have an interface defined, the forces, the fields, are forced to be classified into the components parallel to the interface and perpendicular to the interface. Okay? So whenever we talk about the boundary conditions, we always have two conditions. We always have the parallel, or called tangential, tangent, or the perpendicular one is called the normal. Right? Once we have an interface defined, fields are forced to be divided relatively to the interface into two different components, the tangential component and the normal components. Okay. if you still remember, the first fundamental postulate tells us, do you still remember? A closed loop evaluation of E field intensity is equal to 0, but this is in the integral form. What about the differential form? Do you still remember? The tangential is always coming from the curl relation. Right? The very first fundamental postulate assumes E fields are conserved fields. Therefore, when you make a closed loop integration, it's 0. It's also saying that the E field is conserved. It does not have any curl. Okay. So we have to form a closed loop along these two materials at the boundary, right? So the easiest way to form a closed loop is a rectangle. But I have to make the height, this delta H, extremely small. Why? Look at this evaluation. A closed loop evaluation of my E field intensity means when I form a rectangle, how many sides do I have? I have 4 sides, right? Each side, I'm trying to calculate the line integration of the field with respect to my differential length. So I have one component. This is my tangential field in the second median multiplied by this length, delta W. If I don't make this height extremely small, I actually have to include the normal component of the field inside median number 2 for this part, and the normal component of the field inside median number 1 for this segment, which is very tedious. So the best way is I don't want to include the normal components, and that is fine because I am free to make this height extremely small, approaching 0, but still retaining a closed loop. Okay? So in all these derivations, we have assumed this delta H, the height of the rectangle, is effectively 0. So we're only evaluating this segment and this segment. But in order to form a closed loop, so in this case, the loop direction is following my right hand, right? So I'm using my 4 thumbs to denote the direction of the closed loop. So I only have to evaluate 2 line integrations. The first one is segment CD. It is in the direction of my tangential field inside median number 2. But when I'm trying to evaluate the top segment, the differential length inside the closed loop is now having a reversed direction. Segment A, B is now pointing from the right to the left. Okay? But I have assumed my tangential field inside median number 1 still pointing from the left to the right. So when I perform this integration, I need to include the negative sign for the contribution in median number 1. Okay, so there is a negative sign. So these two adds up to 0. They share the same differential segment length, delta W. So I can cancel that. So in the end, whenever you have boundaries, the tangential part of the E field needs to be continuous. due to the fact E fields are conservative fields. So in the tangential components, even across different materials, they have to be continuous. They have to be the same. Okay? So this is very straightforward. The tangential part of the E fields in different materials, no matter how much you have, right? Even in this case, I have one material, second one, third one, fourth one. The tangential part of the E field, they all need to be the same. Okay? So let me erase this one, and let me just draw the direction again. So this is my E1. So I can actually say this is my ET1, right? This is my tangential component within median number 1. Now that I know, well, the tangential part of the E field in median 1 has to be retained throughout. So I can really just draw, right? I can just draw. Yeah. In O medium, the tangential component has to have the same strength. Okay? Simple and straightforward. Now, if you want to know the angle and the strength, all we have to do is recover the normal components in each medium. So the second condition across a boundary is to find out the normal relationship between the components. Okay? So that is with the help of Gauss's law. As we talked about, well, divergence of D is equal to the free charge enclosed, right? So that means if you form a closed surface and you evaluate the net outward flux, it is equal to the free charge being included. So if we have two medium, medium 1, medium 2, in this case we have to form a closed surface. Now in this case, the textbook is drawing a cylindrical surface, but it's fine. The geometry is really not important. So this cylinder with a very short height, again, this short height is very important because you don't want to evaluate the flux along the sides. You only want to evaluate the flux on the top surface and the bottom surface. Okay? Now remember, the surface normal, when you evaluate the flux, is always pointing outwards, which means I have medium 2 at the bottom, I have medium 1 on the top, but the top is having the surface normal of AN2, the second medium, because this one is pointing out from median number 2. The bottom surface is having the surface normal pointing out, right, from the median 1 to median 2. So this is AN1, right? AN1 equals negative AN2 if the box, the surface is really small, right? So when we evaluate the flux, D1 AN2 plus D2 AN1 times this surface, that's my flux, okay? Because AN1 is negative AN2, so I can just change the sign of D2 and use AN2. So in the end, this is telling you, if you have free charge across the interface, you would have different flux density. Okay? So basically, if you have free charge density surface at the interface, you would have different flux density. Okay? So D1 normal. Why do I have normal? Because everything is dotted to the surface normal. Meaning I'm only evaluating the component parallel to the surface normal. Okay? The tangential part is taken care of already because E1t equals E2t. Here, the Gauss's law is only trying to give you the rule for the normal components. Okay? So a very quick recap. Tangential components for the E field intensity has to be continuous. But for the normal component, you're trying to sense the flux density. Okay? If you have free charge density along the surface, then D1 and D2 in the normal components, they don't have to be continuous. You can have rapid change. Okay? That's the meaning of this equation. So let's take a look at a very quick example. If I have a dielectric conductor interface, conductor means metal, so I have dielectric and metal. And again, we assume perfect metal. So the basic conditions of perfect metal still holds. Inside the metal, I cannot have E field, right? So that directly tells you, well, I cannot have tangential field, even in the dielectric. You still remember? That's what we talked about, right? We talked about if I have a metal, the field can only be in a normal direction. So this again is verified through the boundary condition. Because E2, for example, I'm now defining the conductor, the metal, to be medium number 2. Inside the conductor, I cannot have any field. I cannot have a tangential component. I cannot have the normal component as well. So E2t is equal to 0, and that's forcing E1t to be 0 as well. So whenever you have matter, you cannot have tangential field. But you are allowed to have the normal component. So now you have to think, well, on the interface of a metallic surface, you are allowed to have certain charge density, but still, inside the metal, you cannot have field, right? Not even the normal component. So that's directly telling you D1n is equal to this, and therefore E is equal to D divided by epsilon. Immediately you have this relationship. So this again is verifying if we have metal dielectric interface, even though I can have some charge being deposited, I can only have the normal component of the E field. Because inside the metal, I cannot have any field. Okay? So this is the rigorous proof due to boundary condition to verify that picture. Okay? So that picture is really valid if you have a perfect metal. Right? Second case is probably more practical because whenever we talk about dielectrics, usually we don't have free charge densities. Okay? So these two relations are generic. General applies to all the cases, but now we're talking about special cases. Dielectric conductor, or we have multiple or two dielectrics forming an interface. Dielectrics usually are insulators, so we do not have free charges. So in this case, if I don't have free charge density, that is telling you the D1 normal is equal to D2 normal, right? D1n equals D2n. And therefore, epsilon 1 times E1 normal is equal to epsilon 2 times E2 normal. So let's come back to this case. We have 1, 2, 3, 4 different dielectric media forming 3 interfaces. From the tangential component, we know they are all the same, and we only need to know the normal component. And that is directly given by this relationship, right? E1, epsilon 1, E1n is equal to epsilon 2, E2n, and you can just continue to write down all the equations. Right? You can write 4 of them. Okay? So this is telling you, no matter how many materials you have, no matter how many interfaces you have, once you know your incident field amplitude and your incident angle, you know everything. You know everything because you know the boundary condition. And the boundary condition is coming from 2 equations. First, curl of E is equal to 0. E field is a conserved field. And divergence of D is related equal to rho free. So these 2 fundamental equations tells you a lot. Okay? So in the future, in your examination, I can very irresponsibly just ask you, I give you 10 different materials forming 9 interfaces, and I ask you the outcoming field strength and angle. Right? You're supposed to be able to handle it. Right? But I'm very responsible. I'm not that type of teacher. Okay? So let's go through one example. I have material number 1 having epsilon 1. This is absolute permittivity, epsilon 1. And the second material having absolute permittivity, epsilon 2. I now inject a given E field, E1. Okay? I know its amplitude, meaning the length, and I know its incident angle. The incident angle is the angle with respect to the surface normal. Okay, so this dashed line is the surface normal. And these are 2 perfect dielectrics, so there is no surface free charge density. Okay? So with all this information, you are supposed to be capable of deriving the field strength and the angle in the second medium. Let's start with the easy part. The tangential component needs to be continuous. So this E1t, this guy, has to be the same, right? Has to be the same. So the first equation, E1t is equal to E2t, so that means E1 amplitude multiplied by sine alpha 1 needs to be E2 amplitude sine alpha 2. So this is just telling the tangential part of the E field needs to be the same in the 2 materials. Okay? Now, before we calculate the normal part, well, this is known, but this is unknown. But if the picture is drawn this way, I want you to think, just by looking at the picture, which material is having a higher absolute permittivity? In other words, is epsilon 2 bigger or epsilon 2 being smaller as compared to epsilon 1? This normal component, E2n, is much, much stronger than E1n. So what is your answer? TA, do you know? No? Do you want to answer? Just by looking at the picture, you have to have a very quick conclusion. Material number 2 is having smaller epsilon. Why? Because a smaller epsilon multiplied by a larger normal component will be equal to a smaller field multiplied by a larger epsilon, right? So epsilon 2 has to be smaller. That is one point looking from the math. But have we understood the reason why epsilon is being big? If you have a material with a large epsilon, which means this material is very capable of producing induced dipoles. If you have a lot of induced dipoles, they all try to cancel out your external field, right? By making your field weak. So another perspective, another viewpoint is, well, inside this material, it has a very strong E field. It has a very strong E field because this material is not capable of giving you a lot of induced dipoles, right? So you cannot really cancel all the external field out. So if you have a very strong E field, epsilon will be small, right? So this math is just trying to capture D1n, epsilon 1 times the normal component of E1 equals epsilon 2 multiplied by the normal component of E2. So now you divide the two equations and you can find alpha 2, right? Ideally, incident angle, material parameters are given. So basically, just by dividing these two equations, you can know the angle inside the second medium, the field angle. Again, the angle is with respect to the surface normal. Okay? So now you know the angle. All you need to find is the strength. Well, the strength is actually easy because this tells you the tangential part, and this one tells you the normal part. So you just add them together, square summation, and then take the square root. Okay, so this is purely math. But what I'm trying to emphasize is boundary conditions basically tells you everything. Okay, you know the field amplitude and you know the angle. For one medium, you know the full information, no matter how many interfaces you have. Okay, so this is a very powerful tool, and probably the most practical equations you're learning from this class. Right? Boundary conditions are very important. Okay, one last case, and we close this PowerPoint set. I have a very long coaxial cable. So this is metal, and I have some dielectric filling with relative permittivity, epsilon r, and I have the outer metal, which serves as the ground. Okay? Ground means the potential is 0. So the inner conductor is having a high potential, V0. This is the case we studied previously. Okay? All we have to calculate is, all right, we have field inside the dielectrics. In the previous case, we had vacuum, but now we have a dielectric filling. All right, so ER times 2 pi r equals rho L divided. So this is from Gauss's law again. Okay, we can integrate it, right? So the potential as a function of radius. Again, this is working in cylindrical coordinate, right? This is by definition. Potential as a function is negative line integration of E times differential length, dot with differential length. So that's your answer. For this particular case, because we already know that the inner conductor is held at a high electric potential of V0, so we can replace this R with A being the radius of the inner conductor, and that has to be equal to V0. So V0 is equal to this natural log of B divided by A. B is the radius of the grounding method. Okay? So we can know that the potential as a function of the radius is expressed by this formula. And if you plot it, you are walking from the outer ground and you move closer to the center conductor, you increase your potential. But once you reach to the center conductor, you have the same potential because it's metal, right? Potential has to be the same everywhere. Now look at this result and look at this figure. You have to ask yourselves, now that you have a dielectric filling between the two conductors, what role is that guy playing? You look at this answer, you look at this plot, you don't really know how the material is playing a role in this result. So you ask yourself, what if I increase the relative permittivity of the filling material? What is going to happen? Remember, the material effect is actually included in the potential of the center conductor, right? Epsilon R is included here. So although in the final result, you don't see the material response explicitly, it's actually hidden in here. So when you increase your epsilon R, meaning if you have a filling material which can give you more and more induced electric dipoles, it is weakening the field strength between the two conductors, and thus effectively lowering your V0, right? So if you have a very good insulator with a very high epsilon R, this V0 tends to become 0, right? If you let this guy to be infinite, this is 0. So what kind of material can give you an infinite relative permittivity? Metal, right? Think about it. So if you increase your epsilon R, you expect to have a reduction in your V0, so the entire curve is reduced. In the extreme case, if you have metal connecting these two metal, it makes sense, right? If you have the entire thing as a one piece of metal, they have the same potential. So this V0 needs to be 0. Okay? So again, I'm trying to say that metals are materials which are capable of giving you the most ideal amount of induced electric dipoles. Right? So with that, I conclude this PowerPoint set, and starting from 10 minutes after, we're launching into capacitors. Right? So let's take a break.
解答之后统一公布一个，还是一样要？
他是送都不知道送到哪里，然后对，这是一个问题，干超级白的。对啊，我们订东西啊，然后但是你要讲病毒的东西嘛，
因为他们其实应该也知道
科研事情嘛，病毒，他们知道东西。
应该知道，因为其实他们考完，然后隔天都来问我说，他这个题目
然后就问我在哪里，我就说我在打题目，我反正就干。
应该是他们的语义没有读懂吧？
我觉得那时候我们拿的那个，
就是他的问第二，因为不知道他是跑去问卷，
我知道，
对，那我不太确定。他应该卷和卷不说是没有，应该可能是他的，但是题意他阅读上可能有搞错他的意思。所以照理说，我觉得他们应该知道有4份考卷。
OK， 你的解答在这种情况下应该是要几分？你有没有办法把解答针对他们考的人这样发送？
就是等于就是，
就他只会看到他自己那一份啊。
可以啊，因为就是丢到他们那个资料夹，然后他们自己去看。
好啊，那你就是，好啊，那就4分啊，就代表他们彼此之间不太能够 compare。
可以啊，他们如果找到，他们是找起来不？
不，那他们就自己要算啊，因为你的数字不是直接，你的数字没有那么好转换吧？
就是我不知道，因为式子列出来只是数字带进去，我不太确定。
还是你只是把数学公式列出来，然后，这样就等于是
一个。因为像传输线那题，就等于说你知道一题都要把那个数字给他们。
是啊，你这样子要写好多份哦。对啊。
我想到的话是，可能就写1份，然后我去扫描之后，我用剪下来就好，就个别在卡片上面。
那你不能用打的，然后直接换字就好了嘛？你手写然后剪不是一样吗？
应该是用扫描下来，然后再就是切成几份，然后再贴上去就好了。
随你啦，反正每个人会拿到自己该属于他的解答。好，不回过头的时候4份会不会太多？我在想2份就够了。未来。
可以。你说下一次考试吗
2份跟4，其实你看哦，我们做到是贺佐作用，他们下次知道其实题目不一样，也不会作弊。
对，可是主要也是因为开书考，觉得太作弊了，很无趣。
对啊，开书考了还要作弊，这太丢脸了。对，不，好了，回答你现在的问题是，你可能就是4份解答，然后。就是寄到让他们考这一份的人可以看得到这一份，对啊。好，下次第2次期中考，可能我们就2份就好，对啊。看来他们很棒，考这么差也不用担心他们作弊。
我在想是因为就是因为现在其实人很少，那就15个左右。
什么意思？
就是现在有在线上看。
哦，你只要有一个就还是要。
对，但我在想是因为就是取消小考变成说他们没有一个强迫性，让他们要复习这个礼拜上的东西，变成他们会人的惰性。
问题是开学一开始就跟他们说好不会有小考啦，这没办法，没办法去那个，因为当时其实也没有想到说可以这样线上考。人会有惰性是 OK 的啦，那他损失是他自己啊。 那理论上说录影录下来了，他不见得要课堂上看。对啊，他们不想学，我还是在教啊。对不对？他们也缴学费了，我还是拿薪水，所以自己学习是自己的事。我每次上课都上到录影的人跟助教都在打呵欠想睡觉，我就觉得，
早上吧。
很没成就感。我也知道为什么学生都不想来听。
就一大早上电子学真的。
可是过往上课都是大家都很开心的，很奇怪。什么病？可我自己事后看录影，我觉得看得很爽快。我觉得我教的真是仔细啊。我觉得会有老师愿意讲一个东西、一个观念讲这么彻底的，真不多。这瓶子有梦芬的香水味，显然没洗干净。香水。是。
就是介电系数。
excellent。
对，它那个不是通常是属于介电材质。
对。
可是它金属不是属于磁性。
没有，任何东西只要它有电的反应，它都有一个 epsilon。金属其实它不见得是磁。金属其实有很多电的特性，但我们实验室就是在做金属化学。所以任何东西其实都有 epsilon， 都有 mu。
两个是
对。因为 mu 基本上是告诉你它的磁性的特性，epsilon 是要代表你电的特性。所以只是一般的材料 mu 是等于1 ，mu r 等于1。对，因为一般的材料没有磁性特性。但是磁性材料还是会有电特性。这是个很奇特的。所以即便我们知道什么铁钴镍钴，
他们都比
铁钴镍，它们其实都会有 epsilon 值。对。它们有 mu 值，也有 epsilon 值。那一般的空气啊、塑胶啊，它们有 epsilon 值，没有 mu 值。所以金属基本上。金属先天其实 mu 等于1，频率高的时候，对。然后频率低的时候，可能有一些 mu 不等于1。像你假设说铁磁材料也不是金属，金属就我所知，其实它并没有什么磁的反应。
所以等于说我们要讲的观念更正确来讲，应该要讲说。它是铁材料，就是它是磁还是介电？
对，
正确来讲，
对，也就是说你在看的是 mu 到底有没有什么磁，
对，有没有？
然后 epsilon 有没有什么磁？对。所以一个材料它可以拥有2种特性。真空是2种都有。
只是说这种材料是比较多介电以后是比较多磁表现。
我知道的比较是介电材料 epsilon 都有 response。mu 就几乎没有 response。绝大部分都是。了解。对。哎，你到底是做什么领域的？
我是在做锡箔材料，隐形战机的那种。就是利用 epsilon 跟 mu， 然后让它在里面消弱，然后雷达就不会。
你老师是谁啊？
老师是蔡宏明老师。
他不是机械系的吗？
对啊。
他做这个哦？
没有，就是因为我们输入题目要自己想，然后。
可是这个听起来是 meta material 嘛？
对，就是比较偏材料。
对啊，这是超影材料，这不是严大任老师在做的吗？
对啊，还有那个许文光老师他们在做的。
对啊，我不知道蔡宏明老师也在做这个。
就是实验室，我算是因为算是就是对这个有兴趣，然后第一个做这个。
OK。特别。OK。好了，我们差不多了。某一点。然后不要有。接下来这一节可能不会完成50分钟。
对，谢谢。
now we're moving into the last PowerPoint set of static E-fields. So in this PowerPoint set, we are going to talk about capacitors and electric energy. Right? So by default, a capacitor is the device to store electric energy. Right? Let me try to move this little guy away. Okay. All right. So if we have a capacitor, we use a simple value called capacitance to describe it. So once I have defined a capacitance, we will talk about two particular cases. One is I have a single conductor. A single conductor can also serve as a capacitor. Or we can have multiple conductors to serve as a capacitor. But in the end, I want to emphasize the strategy in evaluating capacitance. And if you still remember, we started with transmission lines, right? A lot of people ask me why I teach transmission line first. Well, the first information is we only need to have scalar processes, right? We don't need to analyze vectors. And the second is, in transmission line, if you still remember, the lumped element circuits are comprised of resistors, capacitors, and inductors. But in there, you just took capacitors, inductors, just willingly, but you don't really know how to calculate the capacitance or inductance for a given transmission line geometry. So the very reason I want to start with transmission line is I give you pretty much a full picture, and then we can nail down the problems one by one as we progress towards the end of the semester. Okay? So if luckily by the end of today, I can show you how much you have improved yourself. All right? Okay, the definition of capacitance is the amount of charge divided by the potential set up by these charges. Okay, so what does that mean? Well, let's take a look at a single piece of conductor. Okay, again, we're dealing with a perfect conductor, so no field allowed inside and no charges are allowed inside the conductor. But you are free to have depositions of charges on its surface. From Coulomb's law, we know that a single charge can set up its own E-field pattern, and if you perform the negative line integration, you have electric potential. So the amount of charges you deposit on the surface of a metal actually gives rise to a total electric potential, right? So when you have charge, you have potential. So the next question is, well, if you have a friend who's very naughty, so now you have 1, 2, 3, 4, 5, 6, now you have 6 charges, right? So this 6 charges together gives rise to certain electric potential. And your friend is donating another 6 charges. And he's asking you, well, if I place these charges, identical charges, very close to your original charges, what is the resulting potential? So this is actually a test to how your metal behaves. So in the ideal case, if you double the amount of charge, you pretty much double the potential as well, right? This makes sense. Okay? So what happens if you triple the amount of charge? Do you need to calculate again? I mean, in the ideal case, you triple the amount of charge, you triple your electric potential, right? Because you are depositing charges onto the same metal, and that metal is acting like a capacitor. Okay? So the physical meaning of capacitance is thus, for a given material with a given geometry, remember, material and geometry, these are the two keywords. When we're dealing with capacitors, it's crucial to understand everything changes once you change the material being used or the geometry being used. Okay? So basically, the capacitance, a single value, tells you whenever you have decided what material to use to fabricate the capacitor and in what geometry. Once you fabricate this guy, it has a unique way to present itself. In a way, if you have developed certain electric potential, that electric potential needs to have how much charge? Or otherwise, if I deposit this amount of charges onto this capacitor, it will give rise to certain voltage value, potential value. Okay? And that unique property does not depend on how much charge you deposit. So once you fabricate the capacitor, you have determined its material, its geometry, that capacitance value is held as a constant. Okay? So it does not matter you deposit the charge amount Q or 2Q. Because whenever you increase the amount of charge, it increases the voltage as well. Okay? So the capacitance value is only a character of the material and geometry. One is decided, it's done. Right? So if we have a simple metallic sphere, a single one, okay, with an inner radius of b, so if I deposit lots of charges onto it, okay, or just a single charge, but now it's uniformly distributed, so this sphere surface is having a uniform surface charge density. So for this guy, what is its capacitance? This is a perfect metal molded in the form of a sphere with radius b. So material is determined, geometry is also determined. Then it should have its unique capacitance value. All right? So how to analyze it? Well, we know that total charge of Q is deposited onto the surface, right? The surface area is 4 pi b squared. So we actually know how to calculate this uniform charge density. Okay. So basically, Q divided by 4 pi r squared, if you're away from it, that's using Gauss's law, right? And we know the voltage. This is nothing new. We talked about it already. Okay. At R equals B, this is where your potential maximum is, right? And that is defined as V0. So all we're trying to seek is, well, we know the total amount of charge is Q, but we're looking for what is the resulting electric potential being contributed by this charge onto the surface in a uniform way. Okay? So all we have to do is we take Q and divide it by V0. And that is the definition of capacitance. So that is 4 pi epsilon 0 B. Starting from this point and on, whenever you try to derive the capacitance value, you always have to bear in your mind your result should somehow show the dependence of material and geometry. Okay? So look at the simple expression. It is correct, indeed, but where is the material response showing up? Where? Right now, you don't really have a way to express the change of material. Well, the perfect metal cannot be replaced, right? Ideally, you don't want to use other things to serve as a capacitor. But something you can change is the ambient, the environment. So in this derivation, what have we assumed? Epsilon 0 represents vacuum. So currently, this metallic sphere is held in vacuum. So if you want to change its capacitance value, all you have to do is immerse it into another medium. Do you need to recalculate the mathematical form of the resulting capacitance? You don't. All you have to do is you add epsilon r, right? So if you immerse this in water, in sugar, in salt, in glass, you don't need to go over the derivation again. All you need to do is incorporate the corresponding relative permittivity of your ambient material. Okay? So that takes care of the material dependence. What about the geometrical dependence? Take a good look. I mean, well, epsilon 0 times epsilon r is the absolute permittivity, and that takes care of the material response. What else do you have? 4 pi b. To your surprise, 4 pi b, the fact 4 pi b is actually telling you you have a capacitor in the form of a sphere. Do you know why? So in the future, once you derive something 4 pi times something, this b is the radius, right? Where is the fact this 4 pi coming from? You have a sphere with a radius of b, right? So the surface area is 4 pi b squared, right? So this 4 pi is coming from the fact your current geometry is a sphere, and B is taking account of its radius. Okay, if you don't believe me, let's continue. All right, so we've taken care of the single capacitor, single conductor capacitor. In our daily lives, usually capacitors are made with multiple or dual conductors. The easiest one, which we will analyze later, is having 2 parallel plates of conductors. But there are capacitors molded in different geometries. If you open up your motherboard for your PC, you can see a lot of these guys. So these are molded in a circular geometry, and they fill with some kind of water, liquid, right? So if your motherboard breaks down, usually it's because of leakage in your capacitor. But at the same time, you see a lot of these guys. So these are ceramic capacitors, but they all serve as capacitors, a way to store electric energy, and later you will understand the capacitors are actually frequency-dependent filters, right? So what happens if we have 2 conductors? It also functions like a capacitor, right? And for these 2 conductors, you connect it with a battery. Okay? Now, usually what it does is, when you connect the battery, you have positive charges deposited on the end of your positive. And you have negative charges deposited over the electrode connected to the negative end. All right? So once you can draw this charge distributions, then you can draw the corresponding E field line distributions. Okay? So if you know the E field distribution, and then you can calculate the resulting electric potential difference. Okay? But my question to you is, at this point, if these 2 conductors are serving as a capacitor, if I remove this battery, will its capacitance change? Think about it. In another way, I'm asking, for a given capacitor, do I really need to connect it to a battery in order to serve or define it as a capacitor? Really, no, because capacitance exists even though you do not connect it, right? If you understand the definition of capacitance is only to say, once you fabricate this guide, it's having its own material and geometry, it has its own capability to draw charge and develop electric potential difference, and that's it. So even though it's not connected, you can still label it with its capacitance value. Right? Okay, so the strategy, so if we have 2 conductors serving as a capacitor, of course, we always need to evaluate the geometry, and we have to choose a good coordinate system to work with. Okay, first step. Then, we can just assume positive charge of Q and negative charge of Q are deposited over on the 2 conductors, respectively. We need to maintain charge neutrality. Okay? charge needs to be neutral. So once we assume there are charges over the conductors, we can calculate the resulting E-field intensity distribution. Okay? Gauss's law is probably most appealing, but if you cannot do it, you can just use Coulomb's law. And once we know the E-field intensity, we perform the negative line integration to find the potential difference between the higher end to the lower end. Okay? So once we have this potential difference, we can just put it in the denominator and we put Q in the numerator, and therefore we have the derived capacitance. Okay? So the procedure is to assume charge Q and negative Q being deposited over the two ends, and then you calculate the E field, you calculate the potential difference, and then you take the ratio of the charge and the potential difference. Okay? First case we're going to analyze is the two parallel plate capacitor. Okay? In these derivations, the assumptions are always made to assume these two plates are very big. What does that mean? It's true. I mean, if the two plates are not really big, then you don't have an easy answer. But I want you to tell me, what does that mean? I mean, physically, if you have two very big plates, this is something you learned. And your second examination is coming up quickly, so you better review. If you have two big metallic plates, you deposit charges onto it, you have positive charge and you have negative charge, you will generate constant E-field patterns. So the E-fields are actually constant. It is not position dependent. Okay? So why do we have to assume the plates are very big? If the plates are not very big, at the edge, right? Assume you have a positive charge and you have a negative charge. At the edge, field start from the positive charge and ends up at the negative charge. So at the edge, your E-field intensity would definitely not be a constant. You will be spatially dependent. Okay? So in all textbooks, we only analyze somewhere in the middle, where you have very uniform and constant E-fields. At the edge, we usually don't talk about it. So that's why in almost all the textbooks, we have to assume the plates are very big. But in reality, we can also say if the separation between the two plates is very small, then the plates are effectively very big. Okay? So we're safe. All right, so if we deposit charge Q on the top and negative Q on the bottom, and we know the plate surface area, so we know the surface charge density is Q divided by S. So we assume we deposited those charges. And in the previous case, we already know that the E fields, in this case, is pointing downwards, right? Fields emit from the positive charge and ends up at the negative charge. So the direction is in the negative y direction. And the amplitude is rho divided by epsilon. This is something we derived already, right? So once we know the E field intensity, all we have to do is perform line integration and remember the significant sign. Okay? So the potential difference between the bottom plate and the top plate is Q times D divided by epsilon and divided by the surface area. This is something we learned already. I bet each and every one of us learned this or memorized research result starting from high school, right? So if you have metallic parallel plates, the capacitance is determined by the dielectric material you use and the surface area and its separation. So again, such a simple relationship, you have to know which one is giving you the material dependence and which one of the parameters are telling you the geometric dependence. Epsilon is definitely material dependent, right? And these two together, the ratio of surface area to the separation is geometry. Okay? So as an engineer, whenever you look at your result, you have to teach yourselves, if you want to change or you want to tune certain value, what to tune. For example, if you have two parallel plates and your first job, after your graduation, your very first job is to make a capacitor with a very high capacitance. But your geometry is limited, right? To have two parallel plates. You want to increase your capacitance. How would you approach it? You remember 3 years ago, the professor taught you such a simple relation, right? You dig out your class note, you look at this relation, epsilon s and divided by d. You want to increase it. So what is the most effective way to increase the capacitance value? If you are limited to the parallel plate geometry. The question might be intriguing, might be misleading. Would you choose to start with epsilon to have different material? Because you think, well, my boss is telling me I have to make parallel plate capacitors, so these two are the geometric dependence, right? I have to fix it, so I have to change material. But if you look up in the tables, epsilon cannot change a lot. Vacuum is 1 times epsilon 0. Silicon, maybe 12. It's probably the best you can have. So you can only increase it by a factor of 12. Right? So tell me, what is the most effective way to increase the capacitance value? Well, epsilon is definitely not the best way to go because you're limited by materials in nature. Okay? So in this case, even though your geometry is limited to the parallel plate scenario, you can either increase the surface area or decrease the separation. So which one is more effective? TA. Increase the surface area or decrease the separation? Yeah, decrease the separation. Why? Because you are an engineer and you're working for a company and your boss wants to save money, right? If you make the surface area very big, your final product will be big, right? And you're using more metal. which costs more and takes more space. So the most effective way is to shrink the device dimension. Okay? So that's the very first lesson for engineers. You have to take into consideration efficiency, which includes money. Okay? All right, second example. Now we have two conductors. This is something we analyzed in the very last page of the previous PowerPoint. This is a coaxial cable, right? I have a center conductor, I have the outer ground conductor. In this case, these two conductors are again filled with a dielectric. So this is actually like the transmission line that we analyzed. This is exactly the transmission line that we analyzed in the very first chapter. But now we have sufficient knowledge to derive its capacitance value. Okay? How to do that? Well, again, we can assume, we don't have to assume because this is such a well-known case. We already know its field value, right? Of course, well, given the length is L, I deposit charge Q onto the central conductor and negative Q onto the outer conductor. I know that all the field lines are in the radial direction. Again, I'm working in the cylindrical coordinate system. So I'm using this lowercase r to denote the radial direction. So this is using Gauss's law, right? 2 pi r. 2 pi r is the circumference of the circle times L, that is the surface area in the radial direction. I enclosed charge of Q, but now I'm inside this dielectric, so this epsilon is really the absolute permittivity. Okay? I integrate that to find the potential difference. So that's my potential difference. Okay? Now, Q divided by the potential difference gives me the resulting capacitance. Again, I want to train you properly. Look at the expression and tell me where is the material response. The material response is capped inside this epsilon. All the rest are the geometrical response. Okay? So if you still remember, in the previous case, we saw this 4 pi b, right? 4 pi b, 4 pi something represents a spherical geometry. And now you have cylindrical geometry, you have 2 pi something. Why? It's due to the fact that your surface is related to the circumference of your circle. It's 2 pi r. Okay? So probably in the future, whenever you see the capacitance having 2 pi dependence, you can guess its geometry is more like cylindrical. And 4 pi something is more spherical. Okay? Now, you should be very proud of yourselves. Why? Well, if you still remember, do you still remember this table? This is something I showed you, right? For transmission lines of different geometries. I showed you each transmission line has its own resistance per unit length, inductance, admittance, conductance, and capacitance, right? Take a good look. This one is the parallel plate. Having two parallel plates is actually a transmission line. And we just analyzed that resulting capacitance. It appears differently because here is per unit length. Okay? So in this case, the coaxial cable, 2 pi epsilon divided by natural log B divided by A. It's just taking this length out. So you have the capacitance per unit length. Okay? So you should be very proud of yourselves because starting from the semester, you were forced to take the concepts of a transmission line being comprised of lumped element circuits. All these components, you just use a symbol, right? R prime, L prime, G prime, C prime, but you don't really know how to formulate all these parameters. But now, gradually, you are capable of deriving the C prime for coaxial cable and the C prime for parallel plate transmission line. You have improved a lot, right? You should be very happy and give yourself some applause. Okay. Okay, the danger is, well, the danger is the thing that the professor does not teach would appear in what? Exams. It's very difficult. Okay, so if you have 2 wires, 2 parallel wires, it also functions like a transmission line. So probably I'll try my best to help you. So either include it in the homework or it will appear in your examination. Okay? So some students might be very happy and excited. Now you can derive 2. So together you have 12. So we only knocked down 2. So we have a long semester to go, right? But eventually, all these can be deduced by yourselves. And that's what I call improvement, right? So now do you see the purpose of teaching you transmission line in the very first place? I give you the entire picture, and then we spend the entire rest of the semester to fill the gap. So you feel your improvement every day, okay? So watch my video closely. All right, so that's for today.